what session I can afford.
Okay, it's 3:05, so let's get started. Just a few things. Quiz 6 is out, due Saturday, you know the drill. Midterm is on Monday. I hope you know that, so I hope you know that. We have review sessions, 2 of them on Friday, 12 to 1:30 at PSH 150, and then a little bit later, 3:30 to 5, same place. So I guess Dr. Coburn will talk about this tomorrow, but the lecture. But the basic idea of these is to send Larry and I, so those are the people that are going to do it, send Larry and I some questions or some things that you feel you're not quite so comfortable on through email, and then we'll prepare some things or bring the questions there, and then we'll try to answer them if we can. Okay? And it's an hour and a half each, so it should be plenty of time to answer all your questions. Any questions before we get started? No.
So, what's the difference between a context-free language and a context-free grammar? Or are they, like, just always connected?
A context-free language is defined to be the language of some context-free grammar. Okay. Just like regular language is the language of some DFA. It's the exact same thing.
Okay.
Yeah. Any other questions? Yeah.
Steps for the CSE.
I'm not going to cover that today. I may cover that on Monday, but then my recitation will be completely full, so I don't know. But, I mean, we can talk about that at the very end. But, actually, no, your questions are more important anyway, so let's do CNF stuff. So what is CNF again?
Chomsky Normal.
Yeah, Chomsky Normal Form. Oh, this pen's so much better, thank you. Normal Form. So what in the world is this Chomsky Normal Form stuff?
It's a way of, like, simplifying a grammar.
Right, it's simplifying the grammar in terms of what? What am I making simpler?
The rule.
Well, variables are still a finite set.
You're refining the rules.
Yeah, making the rules, the structure of them a lot simpler. So, let's see. I need a way of generating the empty string, right? Because I need to get the context-free languages. So, but the way we did it was we restricted you to only do it from the start variable. But we also know that in order to get the context-free languages, we still need to get a single character too. So we're going to allow you to have any variable go to a single term. But again, if we live in this world, it's not going to be very exciting, right? So I need a way of going from one variable to another variable. So how would we do that in CNF? What's that?
Two variables are allowed.
Right, yeah, 2 variables on the right-hand side, and we better make sure that B and C are not the start variable. Okay, and the reason for that is that I don't want to make the empty string in more than one way. Okay, any questions about that? So getting back to the question, can every grammar CFG can be converted into CNF?
Yes.
Yeah, and so what were the steps that we did in order to convert an arbitrary grammar into this?
So first you need to create a new start state.
Yeah, start variable, so a new one, start variable.
And you point it at the
With
original
rule,
start variable with
Right.
rule S. It's like S naught is a new one.
yeah, so at 0 with rule what?
S naught goes to S.
Right, yeah. And the reason for that is that I'm given an arbitrary grammar. I don't want the right-hand side of any rule to have the start variable on it. But if I do this, I didn't change the language, and S0 is not on the right-hand side of any rule. So that's all we need. What's the second step?
You eliminate all epsilon rules.
Yeah, so eliminate. And so this is a little bit deceptive to say eliminate epsilon rules, because I can't just arbitrarily remove epsilon rules, right? Because I could change the language if I did that. So what was the idea that we did for that?
So anywhere in your other rules, if the the rule that you're eliminating, that variable on the left-hand side, if that exists in any other rule on the right-hand side, you can essentially like generate a new rule with that right-hand side with epsilon replaced and all the other combinations of that.
Yeah, so all it really is just simulation of the original epsilon rule without the epsilon rule there. So, I'll do a quick example, I guess. I wasn't planning on this, but let's say that we have A goes to B, little a B, and B goes to epsilon with, and B goes to, does other things other than epsilon. So, what would I have to do here? I want to get rid of this, but I may change the language. So let's simulate all of the possible ways that B could have been empty. Well, could it be possible that both B occurrences here are empty?
Yes.
Yeah. What about if this first one was empty
Then you get
and this one wasn't?
A, B.
Right, I would have another rule like that. What about, I'm just saying, is it possible? Could the second one have been empty and the first one not?
Yes.
Yeah? What about both of them being non-empty?
Yes.
Oh, okay, so the idea is to transform this into keep all of the original rules untouched, but I'm going to add all of the other possibilities where B, the so-called nullable variables, could have been dropped out. So B could have been dropped out, so I could have AB or BA or just a single A. Along with B goes to epsilon and B does the other things. But now I can remove this B to epsilon rule because now it's redundant, because I've just simulated all the possible ways it could have gone to empty. Okay? So now I can axe that rule and then we're good. So then I have no more epsilon rules except for the start variable goes to empty if possible. Okay? Any questions on that? Am I done?
No, you have to.
I'm not even close, so.
So when we say eliminate epsilon rule, it's just adding all possible
Yeah.
rules and just remove the,
And then afterward remove the epsilon.
okay.
So I guess you're not really eliminating it. You're just rewriting the grammar rules. Like you still have
Yeah.
like this grammar here and the grammar on the other side are equivalent.
Yes.
It's just organized differently.
Yeah, I'm just simulating all the possible ways that epsilon could have been made. I'm kind of like shortcutting it, essentially. Yeah.
Okay.
Any other questions? What's the third step?
You have to eliminate the unit
Unit
rules.
rules. What's a unit rule?
A goes to B.
Right. So I have in a unit rule where A goes to a single B. Or essentially a single variable on the right hand side. Okay? Well, how did I eliminate unit rules?
Well, is it kind of similar to eliminating the epsilon rules?
Yeah, there's actually an easier way you could do this. So suppose I had that rule and B goes to A or B A B or A, I guess. So what can I do to fix this? To eliminate that A to B rule? What can I do? Well, what I can do is I can copy all the rules that involve B but are not in a unit rule up to where the unit rule is. So I can erase this and then put all of the rules that correspond to, if I were to take A to B, I'm just shortcutting everything that it could have done. Okay? I need to be more careful if I have more of these, but if I just have a single occurrence like that, I can just copy the things over. Okay? Any questions on that? What's the fourth step?
If you have any rules that have multiple variables on the right-hand side, you have to introduce new variables to break it up so it's in that form.
What's the fourth step?
Oh.
What's the fourth step?
Then what do we have?
Well, I have this problem. How do I fix mixture of variables and terminals problem?
Convert everything to variables.
Ah, yeah. So convert mixes of vars and terminals to just variables. And so the way we can do that is if we have A goes to, I'll do that one up there, BAB, then what I can do is I want the entire right side to be just variables. So what I can do is I can introduce a new variable that produces just that single character. And then what do I do with the first rule? I replace all occurrences of little a with this variable. So use of a right there. Okay. There's a joke I did last semester where I said U of A can only produce a single character. But yeah, that's how you would do it, right? You would make a brand new variable just for that single character, produce that character, and then everywhere that is not just a single character over here, I replace it with that corresponding variable. All right, so then now what's step 5? Bring up the long, well, in general, break it up into long, break up long right-hand side. Okay, well, suppose I had this rule, I'll just copy it. A goes to B, use of A and B. Well, what am I going to do with that?
Create a new variable that goes to UA.
Yeah. So I have a choice. I can either make those first two variables as this new, brand new variable that I'm going to make, or I can make those last two. Either one's okay. So I'm going to do the first two. I'm getting low here. So I'm going to have a variable that makes B UA. So I'm going to call it Y1, and that's going to make B UA. And then up in the original rule, I'm going to have Y1. So all I'm doing is, when I have two variables here, I'm just going to break a brand new variable that makes those two things, and that's it. Okay? Any questions?
Can you re-explain number 3?
Yeah.
At least like how you account for eliminating unit rules?
Yeah. So the idea is, the real way to do it is to make that directed graph thing. But if you have a really simple case like this, where you have just a single occurrence of variable goes to variable, like this, then I have no qualms in copying everything that involves being on the left-hand side and is not a unit rule over here to copy it up to here.
Oh, okay.
It's just all I'm doing is simulation.
What if B is a unit itself?
Right, so if I had a rule like this, then I would need to worry about that. So then what I could do is I could copy C's non-unit rules up there and B's non-unit rules up there. So the correct way is to use the directed graph thing and see whether things are connected or not. But if you have a simple case like this, you can just copy things up, which is what I usually do. It makes it simpler. Any questions about this? So why do we care about CNF? Other than to make you suffer, I guess. Why do we care?
Well, I mean, it makes grammars, I guess, easier to see their structure.
Yeah, it's easier structured, but like, how does it benefit me? Like, if I'm a programmer, how would it benefit me? How many know about first and follow sense?
Yeah. Yes.
Yeah. Turns out, grammars in CNF are much easier to parse for first and follow sense. And another useful property of this, and we'll see soon, is that we can prove languages not context-free with grammars in CNF much easier than ones that aren't in CNF. And actually something that's even more interesting is one of the quiz questions about how long derivations could be for grammar in CNF. So I'll let you think about that. But a lot of useful properties of this. But any other questions? So thank you for bringing that up. Okay, well, I guess we're at the end of whatever I was going to talk about, so let's step back. What was the thing we talked about before CFGs?
Grammars.
Grammars, but what type?
Regular grammars.
Yeah, regular grammars. Okay, so I kind of spoiled all the surprises, but well, I guess we spoiled the surprise. But what things do I have to have in a regular grammar? Or in a grammar in
The
general?
variable.
Yeah, I gotta have variables, right? So I gotta have a set of variables. What else do I need to have?
Terminals.
The terminals, yeah. So like an input alphabet before. What else do I need to have?
A starting symbol?
Starting
variable?
Yeah, start variable. But what else do I have?
Rules.
Yeah, a set of rules, right? Rules. But what makes it a regular grammar versus a context-free grammar?
The rules have a certain structure.
Right,
We only
they
do
have a
one of
certain-
like 3 things.
Yeah, 4, yeah. So what do I want out of the regular grammars? What do I want their property to have? Well, the name implies I want them to recognize the regular languages, right? So what string is in regular languages? In some regular languages, I guess. A simple string. Well, a single character, yeah, that's
Right.
true. So I need to be able to generate a single character, right? If I can't do that, I can't get the regular languages. What's another string that I need? It's even easier. Epsilon, yeah. I need to be able to get that guy, right? Again, if we lived with just these 2 types of rules, it's not interesting. So I need a way of getting to other variables. So I think I should be allowed to go to another variable directly. Just transfer over to another variable and then we're done. But if we live with just these 3, we still can't get anything longer than a single character. Because if I just keep doing replacements like this, I still can only get a single character. So I think I should be allowed to go to another variable and generate a character. Okay? So I should be able to generate a character and go to another variable. So that gives us a lot more power now. Cool. So if I want to show that regular grammars recognize the regular languages, how would I do that?
You can show that there's a bijection between this and a DFA.
That's a great way to put it. Everyone understood that? There's a bijection between regular languages and the languages recognized by regular grammars.
I guess what I can say is you can start a DFA and then make a grammar, and you can start at a grammar and make a DFA.
Right. If I can convert from a regular grammar to something that is that represents regular language, and the other way around, we're all good. Will you let me use an NFA to convert to? Yeah, because we know we can convert that to a DFA. Okay, so are we good with this? Because I'm going to erase it. So I have this NFA that you can hardly see, but is on the handout. So I want to make an NFA out of it. So, well, I got to think about how to convert this thing that has variables and terminals and start variable and rules into something that has states and transitions and final states and all that stuff. So how in the world am I going to do that? Let's see. If you look at any derivation of the regular grammar, how many variables could possibly be made at a single time?
1.
At most 1, right? Can I ever get 2 variables at a single time? No, because I start with a single variable, and every right-hand side has at most 1 variable. Since I'm doing replacing, I can only have 1 variable at any given time. If I look at an NFA, how many states could I be in a computation in an NFA? I think just 1, right? If I'm doing a computation in an NFA, I can only make 1 decision, right? So maybe we can do something similar to that. So let's see. What is the set of variables in this grammar? ST and A, and how did you know that?
Capital.
It's the things on the left-hand side of the rule. All right. what is the set of terminals?
0 and 1.
0 and 1. How did you figure that out?
Well, they're not on the left-hand side.
Well, not on the left-hand side, so I have to look on the right-hand side, but what else do I have to prove now? Well, it can't be a variable, right? So T, A, and S are not going to be counted. What about that vertical bar thing? Should that be counted?
And that's just an or.
It just means or, so it means multiple rules, so it can't do that. What about epsilon?
Never a terminal.
It's never a terminal, right? Just like it wasn't for NFAs and GFAs, it's not going to be here. So I think the only things that are left are 0 and 1. Okay, what's the start variable? And be careful. What's the start variable? You sure? S? Does it have to be S? A? Does it have to be A? Could it be any variable? Does it say that it has to be a certain name over here? No, it's just a certain variable. So I think any one of these could have been the start variable, and I didn't indicate that, right? So we gotta choose one. So I'm gonna choose S for simplicity. I guess that's funny in 2 ways. All right. Anyway, now I gotta make an NFA, right? So I'm thinking, as I'm applying rules, I can only have one variable at a given time at most. So I think maybe I could have that represent what state I'm in the NFA. So maybe we can have states which represent the variables in the grammar. So let's have S, T, and A as variables, as states. What is the start state?
S.
S, good, because it's the start variable. What's the final state? Seems like the only thing that could be one is S, right? It would work in this case, but let's suppose I augmented the grammar with S goes to 0. Well, let's see. If I have some derivation or some computation here, and I land in state S, and I want to apply S goes to 0, what state do I go to? I can't go back to myself, because then that means that I can generate arbitrarily many zeros there. But I didn't say that we can generate arbitrarily many. I can only generate one. So I can't do that. So any other strategy? Maybe we can go to some other state that doesn't represent a variable and make that guy final. Does that sound like a good idea?
That'd be the empty set?
I'm going to a new state that's final.
Okay.
On the rules that have no variable on the right-hand side. Because since it doesn't have a variable over there, I can't go to that state. So that means that the variable must have dropped out, and therefore the only thing I have left are terminals. So I'm going to make a new final state. That's final, obviously. And so now I got to process the rules to figure out what the transitions are. So I see S goes to 0t. So what transition should I add there?
You go from S to T on transition 0.
Yeah, exactly. The really nice thing about the way regular grammars are, especially how they look, is that the rules themselves actually look like transitions. It looks like I'm going from S to T that way on reading a 0. So it's actually really nice in how they actually look. So the conversion's easy. But what about the S to epsilon one? Where should I go on that? The new final state. Okay. On epsilon, obviously. It's because since I can only have at most one variable, whenever I have a way of dropping that variable out, I should have a way of going to a final state and accepting. Okay, what about T to 1A? From where to where? The T to A on 1. Oh, what about T to 0T? Where does that go? Self loop. All right, nothing special there. A to 1S. I think that goes from state A to state S on 1. A to 1A, I think that's a self loop. And A to 0T is from A to T on 0. Very, very simple. All I'm doing is make a state for every variable and a new final state. And for all of the rules that involve a variable on the right-hand side, just make a transition between the corresponding vertices, not vertices, perhaps, corresponding states. And anytime where a variable drops out, go to the final state on whatever that is. Pretty simple. Any questions about that?
So if you didn't have that epsilon there, then we didn't have to add.
Yeah, I didn't have to add that. Oh, good question. Indirectly. If I eliminate that epsilon rule, what's the language's grammar?
It's empty set.
Empty set, right? I can't generate anything, right? So I better have an epsilon there if I wanted to generate anything. But there's nothing wrong with the previous one. Okay. Any other questions? Okay, so let's look at this NFA, and I want to make a regular grammar out of it. So how am I going to do that? Maybe, since it seems like it was so easy to convert over to here and I made so little change, maybe I can go the other way, right? Maybe I can go from this NFA, just reverse this process, okay? So what is my state set in this NFA?
Q0 to
Q0, 1, 2, 3. You know this one now. The input alphabet is obviously the things on the transitions, which is A and B, so that's no problem. What is the start state? Q0, that's pretty simple. And what is the set of final states?
Q0.
Just Q0. So that'll be important in a second. But maybe what we can do is model the transitions of this NFA as rules in the grammar that I'm going to make. Okay, well, let's start with Q0. It's got to produce something. So maybe let's look at all its transitions and see what rules I should add. So where do I go from Q0 on A? Just the Q2. So what rules should I add here? A Q2. All right. Because I'm just representing the states up here as variables now. Well, where does Q0 go on B? Q0, Q1. So how many rules am I going to add?
2.
2. Okay. 2. So B Q0 or B Q1. All right, so we're done with those transitions. So let's do Q1. So where does Q1 go on A?
Q0.
Q0, so I should add A Q0. So where does it go on B?
It doesn't.
It doesn't. So should I add a rule? No, because I'm only concerned with the things that I'm going to generate. I don't care about the things I won't generate. Because for those things, I can't generate them anyway. So there's no reason to put a rule here. Okay? Q2. Q2 on A, where do I go? We go to Q1, so A Q1. I have things on B, so I should go to 1 on B and 2 on B. So B Q1 or B Q2. Oh, what about that epsilon transition? Yeah, we have that other one we haven't used yet. It just goes to a single variable and nothing else. So it actually is, if we allow A to be empty, I don't need to write this down, because if A were empty, then the right side would just be B here.
You're also kind of doing epsilon Q3, but
Yeah,
epsilon
yeah.
concatenated with.
Yeah, that's what I was saying. Yeah.
Okay.
So it's really just doing the exact same thing as before. All right, Q3, what do I do?
Self loop.
B Q3. Yeah. Okay. Am I done? That should give you a hint. My time. I don't think so. Oh yeah, the final state. What's the language of this grammar as is? Empty set. Why? Because every right-hand side has a variable on it. And so I can't generate anything that is just terminals. So what am I going to do about that? Well, let's see. If I see Q0's final state. So if I could end up at Q0, should I be able to drop the variable right then? If I can somehow get back to Q0, should I just be able to drop that variable? Yeah, because if I choose to do that, the string that I have right there, it must have gotten me back to Q0 in the NFA. So, and then therefore I should accept. So I should be able to drop Q0 out from that. Because since we can come back to Q0, I should be able to drop it out. Okay. Any questions about this? Yeah.
So if like Q1, let's say, was the final state, then we would just add Q1 also goes to epsilon.
All 5 other recitations ask the exact same question. So I guess it's really important. But if Q1 was also final, I would add over epsilon there. So all the cases where it's the final state, if I am able to end up there, then if I choose to drop that, variable, then the corresponding string that I have so far, that's accepted by the NFA because I got to that state somehow. But only for the final states here. All right, but the essential idea is clear, right? Basically, represent variables as states and rules as transitions, and the other way around. Okay? Any questions about that? Okay, well, what was the step up after regular grammars?
Context-free grammars?
Yeah, context-free grammars. And so I guess we kind of know what those look like, but it's useful to go over it again. So we have context-free grammars. So what changes from being a regular grammar versus a context-free grammar? What changes? Well, it's a grammar, so I don't think we should change the fact that we have variables and start variable and terminals, right? I gotta generate a string, right? So I think the rules are gonna change. So what changes about the rules?
It can be anything, as long as it's a combination of terminals and non-terminals.
So something, we should generalize things a little bit. Well, I see this word context-free there, and that seems like to me, if I have a variable to replace, it doesn't matter what's on the left or right side of that variable, right? So what's the thing that I should be replacing? I think it's just a variable, right? So I think the left-hand side should always be a variable because it's context-free. So what should be on the right-hand side then? If I want to generalize as much as possible. Maybe I should allow us to have arbitrarily many things on the right-hand side. Any combination of variables and terminals, because I can't stick to just this because I want something more than regular languages. So I'm going to allow you to go to anything. So W where W is a variable or a terminal, but any combination and as many as you want. Okay? So as general as we possibly can. And obviously we can have epsilon on the right-hand side too. Okay, so let's start making CFGs. So the first one is palindromes. So if we have everything in 0, 1 star, W is a palindrome. First off, is this language regular?
Can you prove it wasn't?
I don't think so. What string should I use? Yeah, so that string would work. 0 to the P1, 0 to the P. Well, that's clearly a palindrome and length of least P, so at least we can start doing that. Where can I pump in that string?
In the first P.
In the first P
Ps.
characters, right? So if I pump more things into there, the middle of the string was the 1 right there, right? But if I pump more things into here, the 1's gonna move onto the right half. But if that happens, then the first half only has zeros, but the second half has 1. So therefore it can't be in the language, and therefore it's not right. But I want to make a CFG for it. So how am I going to do that? It doesn't seem immediately obvious, so I'm going to suggest a strategy which I call recurse, then base case. So here's the idea. Let's pick a string in the language. So I'm going to call it W1, W2, W3, n-2, n-1. So I assume right off the bat that this thing is a palindrome. So is there anything that I can infer about this string from the fact that it's a palindrome?
W1 equals Wn.
Ah, yeah, W1 is equal to Wn, right? Because it has to read the same forwards and backwards. Oh, what else can I say? Ah, W2 and Wn-1 are the same also. Okay. And that's obviously going to be true for the rest of the string going inside. Let's see. Suppose I did this. Suppose I took off the first character and the last character of the string. What's the resulting string? Is also a palindrome. Ah, so maybe what I can do in my grammar is I can chop off the character at the beginning and the same character at the end, and the thing in the middle better be a palindrome. Ah, so that's pretty useful. But if I do that, I need to get down to some base case, obviously. So what's a base case here? Just a single 0 or 1, so I'm going to write this. So base case is 0 and 1. Is there another one? Epsilon, right? In the case where I start off with an even length string, I take 2 off, and then I eventually get down to 0. Okay, so that seems like a good idea. So luckily for this grammar, we're going to have only one variable, which is nice. So here's the idea. So I'm going to knock off a character at the beginning and the same character at the end. So I'm going to take a character off, and I better take off a 0 at the end because I want the same character. What should go in the middle? S, right? So I'm thinking S generates all palindromes. The thing in the middle better be a palindrome too. Okay, well I better do the same thing for 1 because I may have, it starts in as 1 too. So those are my recursive cases. So I need now rules for my 3 base cases. So I need a 0, 1, and epsilon. Cool. Is there a regular grammar for this language? No, and how do you know? It's not a regular language. So the amazing thing about this is that it's almost exactly the same, right? The only rules that cause a problem are here. And so just that simple modification gets me a non-regular language. So that's pretty shocking. But suppose I wasn't so clever about my base cases. Suppose I added on to this, S goes to 0, 0. Is this still in the language? Still the same language?
Sure.
Yeah, because 0, 0 is a palindrome, and it would have been made by S goes to 0 as 0, and then that S is replaced with epsilon. But did I do anything to this grammar?
You made it ambiguous.
I made it ambiguous. Exactly. What is the meaning of ambiguous? Ah, yeah. 2 or more leftmost derivations. In this grammar, do I have leftmost derivations all the time?
Mm-hmm.
Yeah, because I start out with a variable, and I can only have at most one variable on the right-hand side. So I can only have a single variable to replace. So I always have a leftmost derivation. But I have a string 0, 0 that is generated in two different ways. Do I care about the string 0, 1 if it can be generated two ways? No. Is 0, 1 in this language? No. So what strings do I care about whether they have multiple derivations or not? Do I care about the ones not in the language? No, only the ones in the language. But I call this grammar ambiguous, but did I need to check every string or just one? Ah, so only some string in the language can be generated either by two parse trees or two leftmost derivations. Nice. But let's say we stuck with the original grammar that we had. Is this grammar ambiguous? Well, let's see. How many ways can I make the empty string?
One way.
Exactly one, this way. I can't use any of these four rules because they always generate a character. So I can't use those. What about a single length string, a single character string? How many ways can I make that?
2.
Well, once I fix a string, how many ways do I have? One, right? It's either going to be 0 or 1, but I can't apply both of them once I have one of those. Okay, so I have one way to make those. What about anything of length at least 2? How many possibilities once I fix the string do I have? 1, right? It's going to be one of those two. Can't be any one of these three. So every single string in this language can only be generated exactly once with this grammar. So the exact same language can have an unambiguous grammar and an ambiguous one, but not necessarily the other one. Okay. Any questions about this? All right, so let's do one more, then I'll ask important questions after. Okay. So this language is a little easier. 0 to the end, 1 to the 2 end, and it is. Is this regular or not? Did I say the right answer? Is this regular?
No.
No, thank you. What string should I pick?
0 to P, 1 to 2P.
0 to the P, 1 to the 2P. And that's obviously going to pop out. But I want to make a context-free grammar for it. So how am I going to do that? Maybe I can use this cross-off and recurse kind of idea. Well, for the strings in this language, I kind of know what they look like. It's just zeros followed by ones. So let's see. So a string in this language has a bunch of zeros followed by a bunch of ones. Could I apply this recursive idea to this string?
Mm-hmm.
Yeah, how would I do that?
Well, you know that there has to be some kind of middle kernel element.
Yeah, but like to get to a smaller string, what would I have to do?
1, 0, and 2, 1.
Ah, yeah. If I cross off a 0, I need to cross off 2 1s at the end. And we know now that the resulting string better be in the language, because if I take off 1 off of the number of zeros, I must take 2 off the number of ones. Okay, so that seems like a good idea. But now, again, I need my base case. So what's the base case for this? Epsilon, right? Because once I get down to 0, 1, 1, then I can apply this again to get epsilon. So it's actually an easier grammar now. So I need my base case, epsilon. Or I chop off a 0 off the front. I take 2 1s off the end, and then I recurse. Very cool. So we even went down from 5 rules down to 2, and we still have a non-regular language. So I think that's still pretty interesting. Any questions on how we were able to do that? But so now let's ask important questions. What is the relation between regular and context-free languages? What's the relation? I'll ask it in 2 different ways. Is every context-free language regular? No, how do you know? We just showed 2 examples. There are actually many more, but We showed at least one. So not every context-free language is regular. What about the other way?
Every regular grammar is context-free.
Ah, yeah. Let's think about it. What do we know about regular grammars that we were just doing? We can convert back and forth between N and base. So what languages do regular grammars recognize? The regular languages. Ah, is every regular grammar a context-free grammar? Yeah, how do you know that?
Because we can make context-free grammar.
Well, is it already a context-free grammar? Yeah, because it's just a restricted set of rules. It doesn't say I had to use complex rules. It's already a context-free grammar. So every regular language is context-free. Ah, so that's pretty nice. It's a strict subset of the context-free languages because we have some that are not regular. Cool. Any questions about that? Okay, so I have a few minutes, so let's do some of the questions on the back.
So why do we care about the ambiguous grammar? Why do we care whether the grammar is ambiguous or not?
Yeah, why do we care about ambiguity? Because if, for example, if I was deriving, seeing if a program, an input program was in the language of some context-free grammar for a programming language, then I want to be able to derive that conclusion unambiguously, if possible. I don't want to have multiple ways of deriving the same thing. Because if I have only one way to derive it, then parsing it is much easier. And actually the algorithms for parsing are vastly faster when you have an unambiguous grammar. I'll let you look that up, but it's actually pretty interesting, the difference between those two. But yeah, any other questions? Okay, so let's look at the questions on the back. So it says, if G is a CFG in CNF, what's CNF? Chomsky Normal Form, good. Then it is ambiguous. So if I have a grammar in CNF, then it must be ambiguous. Is that a true or false statement?
False.
Yeah, false. And what's the counterexample? Very, very easy counterexample. Yeah.
What about A goes epsilon?
Yeah, S goes to empty. Right? Is this in CNF?
Yes.
Yep. Is it ambiguous?
No.
Nope. So I found a grammar in CNF that is unambiguous. So that statement is false. Next one. Every CFG not in CNF, so it's not in CNF, remember, it is not a regular grammar. So every CFG not in CNF is not a regular grammar. Any counterexample, or do you think that's true?
You can convert anything to a Chomsky Normal Form.
Yeah, but I'm talking about the existing grammar itself right there. The actual structure of the grammar.
So if you have a context-free grammar, it's not guaranteed to be regular.
The structure is not guaranteed to be regular. But could I have it where I have something not in CNF, but it is a regular grammar? Could I have that scenario?
Yeah.
Yeah, what's an example?
Any grammar?
Almost any grammar. So here's one. I can't quite do S to epsilon because this isn't CNF. But so now I need one that's almost like it, but it's not in CNF, but it is regular. So here's an example. Right? This is definitely not in CNF because this better be the start variable. But even if it wasn't the start variable, it's still fail. So this is definitely not CNF, but is it a regular grammar? And yes, it's true because it applies this type of rule and this type of rule. So it is, so that statement's false too. I guess we can try one more. I actually haven't done these with the recitation yet, so you'll see it for the first time. CFLs are enclosed under union, concatenation, and star. Is that a true statement? I'll do union first. it turns out to be true for all three, but suppose we have L1 and L2, which are CFLs. So I'm going to say G1, G2 are the CFGs, the corresponding ones. And with start variables, S1, S2. Okay. Could I form the union of these? And I'm going to suggest an idea that's very similar to union for NFAs. So what I'm going to do is make new start variable S with what rule do you think I should add? S to S1 or S2. Right? Because for union, I could either choose to go pick a string in S1 or I could have went through S2. And so there is a subtle difference here that with no variables in it's a subtle thing because I don't want to go into S1 and then switch over to something in S2, the second rank. But the idea is clear that I need to choose one of the two. Okay? So I'll let you think about the other two, but any other questions? All right, I'll see you next week. Oh, go ahead, sorry.
We can create an essay from this and do a union from that also. So it's kind of
It's the same idea, but I got to work with the grammars so far. We will have a machine model for these, but for grammars as is.
So because you have them as CFLs, I thought there was no guarantee that you have NFAs for them because you don't know if they're regular or not.
Right, I said CFGs, but the idea is the same of like doing epsilon transitions in. I'm doing rule application without generating anything. It's the same idea.
Okay. Oh, okay. So you're unioning the languages together and showing that you're still in a CFG.
Yes. And then copy and paste all the rules,
Right.
but yeah.
So the idea that you're closing a union here for CFLs, meaning if you take two CFLs, concatenate union or star them, you still get a CFL.
Yes.
Okay.
Any other questions? All right, I'll see you next week.